Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture we solved couple of problems on shear strength of soil. Today we will be taking another few problems. So, today's first problem is a sample of dry coarse sand is tested in the lab triaxial apparatus in the undrained condition under a cell pressure of 2 kg per centimeter square. The sample failed when the deviated stress reached 4.38 kg per centimeter square. Now, determine the shear parameters of the soil. As I told you, shear parameters means C and phi. At what deviated stress will the soil fail if the cell pressure be 3 kg per centimeter square? Okay. So, under the cell pressure of 2 kg per centimeter square, the soil failed when the deviated stress reached at 4.38 kg per centimeter square. And now, we are going to solve this problem. The first, so problem 22. So, here sigma 3 is equal to 2 kg per centimeter square. Sigma d, that is deviated stress, is 4.38 kg per centimeter square. Therefore, sigma 1, that is the major principal stress, will be sigma 3 plus sigma d, as we know, that gives me 6.38 kg per centimeter square. Okay. Now, we are going to draw a Mohr circle. Now, a Mohr circle is drawn considering this situation. So, tau sigma space. Okay. So, this is the Mohr circle. Okay. Now, since the sample is made of coarse sand, as it is given in the problem, dry coarse sand, you are using. Since the sample is made of dry coarse sand and since it is in the dry state, right. So, no apparent cohesion will be coming into the picture. So, you will be getting cohesion is 0. So, therefore, the Coulomb failure envelope will pass through the origin, right. If C is 0, so there will be no intercept on the tau axis. So, your Coulomb failure envelope will pass through the origin, right. So, now this is the Mohr circle, this is your sigma 1, this is your sigma 3. Now, one thing we have decided, because you are using the dry coarse sand, therefore, C is 0. So, the Mohr Coulomb failure envelope will pass through the origin. Origin means this point, and it will be tangent to this Mohr circle, right. Otherwise, it will not be, the Mohr circle should touch the failure envelope, then only it will be the Mohr circle corresponding to the failure of the sample. So, it will be tangent to the Mohr circle at failure. So, this is a center of the Mohr circle, say C. This is the point where the Mohr circle is touching the failure envelope is D, and this is the origin O. And so, therefore, this angle is phi. So, you need to find out the magnitude of phi, because C is 0. So, we can, if you look at this figure, we can write down OC is equal to sigma 1 plus sigma 3 by 2, right. What is OC? OC is the distance between the origin and the center of the Mohr circle. So, that is nothing but sigma 1 plus sigma 3 by 2, which is 6.38 plus 2 by 2 is equal to 4.19. Similarly, CD, what is CD? CD is nothing but your radius of the Mohr circle, right. CD is the radius of the Mohr circle, which will be making an angle 90 degree at the tangent point. Okay. So, CD is equal to sigma 1 minus sigma 3 by 2, which is equal to 6.38 minus 2 by 2 is equal to 2.1. Okay. Therefore, from the figure I can write sin phi is equal to CD bar by OC, right. CD by OC is your sin phi. So, which is nothing but 2.19 by 4.19. So, from this I get phi is equal to 31 degree. Okay. So, therefore, your C is 0. What are the shear strength parameters? C is 0 and phi is 31 degree. Okay. So, now we have seen that how I can find out the shear strength parameters for this arrangement, like when your cell pressure is 2 kg per centimeter square and the debitory stress at failure is 4.38 kg per centimeter square. Now, we will go to the second part. In the second part, it is asked that at what debitory stress will the soil fail if the cell pressure is 3 kg per centimeter square. So, in the second part, we know that sigma 1 is equal to sigma 3 tan square alpha plus 2 c tan alpha. So, as your C is 0, so this term will be becoming 0. So, therefore, I can write sigma 1 equal to sigma 3 tan square alpha, okay. So, which is nothing but sigma 3 tan square 45 degree plus phi by 2. Okay. Now, in the second part it is given sigma 3 is equal to, that is the cell pressure is becoming 3 kg per centimeter square, and already we have calculated phi equal to 31 degree, because you are dealing with the same sample, just you are varying the cell pressure. So, phi will not be changing, right. Phi cannot be changed, cannot be varied with the variation of the cell pressure, right. So, phi will be remaining same whatever you have got with some other cell pressure, that is 2 kg per centimeter square earlier. Okay. So, from this I can find out sigma 1 is equal to 3 tan square 45 degree plus, so which gives me 9.37 kg per centimeter square. So, you have got the major principal stress corresponding to the cell pressure 3 kg per centimeter square, okay, at failure. So, if this is the major principal stress at failure, then you can find out the deviator stress is nothing but sigma 1 minus sigma 3. So, sigma 1 minus sigma 3, which is nothing but 9.37 minus 3 is equal to 6.37 kg per centimeter. So, if you go, so if you increase the cell pressure as 3 kg per centimeter square, then you have to apply 6.37 as deviator stress to get the failure, okay, for the same soil. So, we have solved this problem. So, I hope that you have understood the concept and how we are using the parameters and how we are playing with the parameters. I hope that you have understood. Now, we will take the second problem. The problem says the shear strength parameters of a given soil are C equal to 0.26 kg per centimeter square and phi equal to 21 degree. Undrained triaxial tests are to be carried out on specimens of this soil. Determine first deviated stress at which failure will occur if the cell pressure be 2.5 kg per centimeter square, and the second part the cell pressure during the test. Determine the cell pressure during the test if the sample fails when the deviated stress reaches 1.68 kg per centimeter square. Okay. So, now again this is pretty simple problem, already we have solved. So, we know sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha, right, for the given soil. C equal to 0.26 kg per centimeter square and phi equal to 21 degree. Therefore, tan square alpha will be 2.117 and tan alpha will be okay. Now, hence sigma 1 is equal to 2.117 sigma 3 plus 2 into C, C is 0.26. So, and tan alpha is 1.455. So, that gives me sigma 1 is equal to 2.117 sigma 3 plus 0.757. So, I am calling this as equation 1. Now, when your sigma 3 is 2.5 kg per centimeter square. So, that is the first part that determine the deviated stress at which failure will occur if the cell pressure be 2.5 kg per centimeter square. So, if the cell pressure becomes 2.5 kg per centimeter square, then I can find out sigma 1 from equation 1 as 6.05, right. You place sigma 3 equal to 2.5 and you get the magnitude of sigma 1 from equation 1. So, once I know sigma 1, then basically deviated stress sigma d is nothing but sigma 1 minus sigma 3, which gives me 3.55 kg per centimeter square. Okay. So, hence the required deviated stress is 3.55 kg per centimeter square to get the failure with cell pressure as 2.5 kg per centimeter square. Now, in the second part, let the required cell pressure be x kg per centimeter square. So, therefore, sigma 1 is equal to sigma 3 plus sigma d is equal to 1.68 plus x. What is 1.68? 1.68 is deviated stress. Okay. So, if you apply, if you get the failure at deviated stress 1.68, then what will be the cell pressure? That is the question, right. That is the second part of the problem. Okay. So, I have got sigma 1 is equal to 1.68 plus x. Now, I put that thing in equation 1. So, I have got sigma 3 which is nothing but x kg per centimeter square and sigma 1 which is nothing but 1.68 plus x kg per centimeter square. Okay. So, I will put that thing in the equation 1. So, 1.68 plus x is equal to 2.117 x plus 0.757. So, from this I will get x, which is nothing but your required sigma 3, which is nothing but 0.83 kg per centimeter square. Okay. So, I hope that you have understood the problem. Very straightforward problem, right. So, you have got the shear strength parameters, and you are finding out that how much pressure you need to apply to get the failure. Now, we will go for the next problem. So, next problem says the following are the results of a set of drain triaxial tests performed on 3 identical specimens of 38 millimeter diameter and 76 millimeter height. Determine the shear parameters of the soil. So, you have done some drain test on 3 identical specimens of this size 38 millimeter diameter and 76 millimeter in height, and you need to find out the shear strength parameters. So, sample, there are 3 samples, sample 1, 2 and 3. So, you have got the cell pressure, different cell pressure 50, 100 and 150 kg per centimeter square. You have got the deviator load. Okay. So, basically you are calculating, or you are reporting the deviator load at failure is 0.0711 kilonewton and so on. Change in volume. So, when you are applying, because you are doing the drain test, so you will be observing some volume change, because consolidation is happening, right. I mean, you will be getting the water will be draining out. So, you will be getting the volume change in during the shear. So, you have got 2 different say stages, right. One is in the first stage you do the consolidation, and second stage you do the shearing. Okay. So, you have got the change in volume, and you have got the axial deformation also. So, that is 5.1 millimeter for sample 1, 7 millimeter for sample 2 and 9.1 millimeter for sample 3. Now, let us do this problem. So, problem 24. The deviator loads at failure corresponding to each cell pressure are given. Okay. In order to determine the corresponding deviator stress, these loads are to be divided by the corrected area. Why corrected area? Because when you are considering the shearing, that means the volume change you are considering. So, I mean you may get the decrease in the volume or increase in the volume, right. Whatever may be the situation, you will be getting the volume change. So, when the volume change is happening, so you will be getting the area, whether it is bulging or contracting, depending on that you will be getting the different areas at different deviatory stress. So, you need to correct the you need to find out the actual area on which the deviatory load is acting, and based on that you can find out the deviator stress. Okay. So, by the corrected area of the sample, which can be obtained from this equation. AC is equal to V1 plus minus delta V divided by L 1 minus delta L. Okay. So, where V 1 is the initial volume of the specimen, delta V is the volume change. Now, it could be additive, it could be subtractive, depending on whether you are getting the increase in the volume or decrease in the volume. So, already you have seen that if you consider the dense sand, you generally get the increase in the volume, right. At that time delta V will be additive. So, if you get the decrease in the, most of the times you will be getting the decrease in the volume. So, then your delta V will be subtractive. Well, L 1 is the initial length of the specimen and delta L is the change in length or the axial deformation. Okay. So, now your V 1, that is the initial volume of the specimen, is pi by 4 3.8 square. So, 3.8 centimeter is the diameter and 7.6 centimeter is the length. So, cc, which is coming as 86.19 cc. So, L 1 is 7.6 centimeter as given in the problem. So, for the first sample, your delta V is given as minus 0.9 cc, okay, and your delta L is given as 5.1 millimeter. Okay, that is given in the problem. You see the table, you will see that. Therefore, AC corrected area will be 86.19 minus 0.9 divided by 7.6 minus 0.51, okay, which gives me 12.03 centimeter square, which is nothing but 12.03 into 10 to the power minus 4 meter square. Okay. Therefore, your sigma d, that is deviated stress, is now the deviated load by the corrected area. So, deviated load is given as 0.0711 kilonewton by 12.03 into 10 to the power minus 4 meter square, that is the corrected area, which gives me 59.10 kilonewton per meter square. So, therefore, sigma 1 is equal to sigma 3 plus sigma d, which is 50 plus 50 is the cell pressure, that is nothing but sigma 3 for sample 1. You see that thing from the table, plus 59.1 is equal to 109.10 kilonewton per meter square. So, now we will complete the calculations for other two samples. So, if I make the table something like this, where you have sample, then sigma 3 in kilonewton per meter square, then deviated load in kilonewton, then volume change in cc, then axial deformation in millimeter, then corrected area in centimeter square, then sigma d, that is the deviated stress in kilonewton per meter square, and then sigma 1 kilonewton per meter square. Okay. So, for sample 1 already we have calculated, we are just putting the values. So, I did not calculate the values for other two samples, however, you can calculate all those things by following the similar procedure whatever we followed for sample 1. So, sample 2 is 100 0.0859 minus 1.3, 7, 12.36, 69.50, 169.50, and for sample 3 cell pressure is 150, deviated load is 0.0956, volume change is minus 1.6, axial deformation 9.1 millimeter, corrected area 12.65 centimeter square, deviated stress is 75.61 kilonewton per meter square, and sigma 1 is equal to 225.61. Okay. So, this is the table we have completed. So, once we get this table, now you can calculate the shear strength parameters by graphically as well as analytically. So, I will give you the hints for the analytical solution. However, we will see that how you can get this graphically. So, tau, this is sigma. So, basically you will be getting 3 more circles, so if you draw all the more circles, okay, this is for sample 1, this is for sample 2, this is for sample 3, this is your sigma 1 for sample 1, this is for sigma 1 for sample 2, this is for sigma 1 for sample 3, and so on, right. This is for sigma 3 for sample 1, sigma 3 for sample 2, sigma 3 for sample 3. Okay. So, you will now this is the, these are 3 more cycles for 3 different samples, but they are identical. So, they should give you the same shear strength parameters, right. So, you will be getting a common tangent, okay, which will be acting as a Mohr Coulomb failure envelope. So, this is your common tangent, this is the phi and this is the C value. So, graphically if you solve, that means to the scale if you plot, so you will be getting C equal to 25 kilonewton per meter square and phi equal to 3.80. Okay. The same problem can be solved analytically also. Analytically also means, say you know sigma 1 and sigma 3 combination, right, for all 3 samples. So, you will be able to, I mean you know sigma 1 is equal to sigma 3 tan square alpha plus 2c tan alpha, that equation you know. So, in that equation if you put, okay, sigma 1 and sigma 3 for sample 1, for sample 2 and sample 3, you will be getting 3 simultaneous equations, and if you solve these 3 equations, you will be getting C and phi value. So, already we have solved similar kind of problem earlier. So, if you follow that thing without graphical plot, you can get the value of C and phi. So, I will stop here today. Thank you very much.